This is not on the quiz tomorrow. Alright, 2.5, not on the quiz tomorrow. Implicit differentiation. Okay, so first let me explain to you what this is. Alright? It says the equation y equals 3x squared minus 7x plus 5 is expressed in explicit form. Okay, in other words, y equals. So far this year, the only things I've asked you to find derivative of were in y equals, and then your answer was basically y prime equals. Okay? Well, that's going to be new. This is going to change today. So here we have this equation. All right? You don't have to know what this makes. It doesn't really matter. Well, I'll tell you. It makes this graph down here. But this equation is what we call implicit. In other words, it's not in y equals, and if we were to try to get y by itself, it would be very difficult, if not impossible to do. All right, have you ever seen equations that look anything like this, where you have x squareds and y squareds? Circles, ellipses, hyperbolas, sideways parabolas. So you actually have learned about these kind of things. They're not functions, and these are what we call implicit equations. All right? In order to take the derivative of an implicit equation, we're going to use a strategy called implicit differentiation. All right? Now, we've been using y prime a lot lately. I'm really going to focus on dy over dx. The reason is y prime looks an awful lot like y. And if we're using y prime with what we're doing today, it's going to get confusing because we're going to get the y primes and the y's mixed up. So we're just going to use this convention where when I'm talking about the derivative of y, I'm going to use dy over dx. What this means is the derivative of y with respect to x. In fact, everything we've taken derivative of so far this year has been with respect to x. Do you remember when we learned how to plug a derivative into your calculator? And you wrote the expression and then you wrote comma x, right? That's because you were deriving with respect to x, okay? And so this isn't a brand new thing. We've been doing this the whole time, but we're putting a name to it now. So it says when you differentiate terms involving only x, you just differentiate as usual. So we're going to treat x the same as we treated it this whole time. But when you differentiate terms involving y, we're going to use the chain rule. Okay, so let me go ahead and do an example. All right, and I'm not actually going to do example 2 today, and we might get to it another day, but if you want to scratch that out, you can, because I'm going to end up writing pretty big, so it'll take up this whole page. You can write as big as me, or you can try to make it fit right here. It's up to you. So this was the equation we just saw, and they want us to basically find y prime, or the derivative of y with respect to x. We have to do this with implicit differentiation because we can't get y by itself. If we could get y by itself, we would, and then we just do what we've been doing so far, okay? But it's not that easy, all right? By the way, this is the shape it makes. I'll refer back to this at the end, all right? But we don't need the graph, really, to do implicit differentiation. Okay, so there's going to be 4 steps that we're going to follow, all right? And as I get into this, these problems are not short. There's quite a bit of writing to do, and it's not that bad, but it's going to look really crazy. So just giving you a warning now. Don't zone out and then come back to me 5 minutes later because it's going to look crazy. All right, so what we're going to do first is we're going to take the derivative of both sides. D over dx means take the derivative of both sides. All right, so this is what I mean by that. We're going to do d over dx of the left side, and I'm also going to do d over dx of the right side. You could rewrite that whole line if you wanted to, but it's already typed there. We might as well just do d over dx in front of the type. Okay, if you take the derivative of both sides, you retain the equal sign, everything's fine. It's kind of like when we're squaring or square rooting or adding something to both sides. It's like that. So let's take the derivative. What do you think the derivative of y cubed is? 3y squared. You're almost right. I mean, you are right, but there's just one more thing we need to add. Y is its own function. So it's kind of like the M&M. We took the derivative of the shell, now we have to take the derivative of the chocolate. In this case and in every case, that derivative is always going to be dy over dx. And what that just means is y prime. Okay, so let me explain this again, but most of you are just going to get used to just, oh, when you take derivative of y, write this. Okay, so I took the derivative of y cubed, all right, 3y squared. Now I have to take the derivative of the inside, and that name is dy over dx. That's what the derivative of y is. So it's like using the chain rule. That's what the directions or the print up at the top said we're going to have to do anyway. Okay, but when we take the derivative of an x term, we don't have to worry about this. So what's the derivative of x cubed?
3x squared.
3x squared. We don't have anything else we have to write for that. Okay. Next, we have another y term. So again, what's the derivative of negative y squared? Yeah, minus 2y. And since this is a y term, you have to write dy over dx next to it. Anytime you take the derivative of a term involving y, you've got to write dy over dx. That's because y is its own function. All right, whereas x is what we're taking derivative with respect to, okay? And we haven't had to do this yet because we haven't had to take the derivative of y mixed into the problem. That's why we've never seen this before. Okay, well, what do you think is going to happen next? What's next?
Minus 5 is dy over dx.
Yeah, minus 5, because that's the derivative of negative 5y. And since there was a y term, we're going to write dy over dx.
So you still have to do it even if the y disappears?
Correct. Even if the y is not there, you still took derivative with respect to y, so you have to write that. All right, and then what's the derivative of negative x squared?
Minus 6.
Negative 2x, or minus 2x. Okay, the right side is going to actually be easier. What's the derivative of any number? 0. That's not changing, or will it? Okay, so this is what I was saying. This looks pretty crazy, but I want to remind you that these little dy over dx's, this is just a term, and we could be using y prime in its place, but again, y prime looks an awful lot like y. And if I already have a y here and a y squared here, y prime, I might not really know where those are. And these three things are very distinct. So if you haven't circled them like I have, I want you to go ahead and do that. Because this is going to be my next step. My next step is I want all of the dy over dx, I want all of those terms on the left side. And I don't want anything else on the left. I only want the dy over dx terms. What I'm working towards is getting dy over dx by itself. Okay, that's what we want for our final answer. So one way that I'm going to get there is to write all of these terms on the left side. And so I'm skipping over plus 3x squared. I'll get to that in a minute. It's not going away. I'm just going to move it. Okay, so now I only have dy over dx terms on the left. All right, anything that doesn't have a dy over dx connected to it, we're going to move it to the right side by adding and subtracting. All right, so first, just plus 3x squared on the left, we're going to subtract that over so that it becomes negative 3x squared on the right side. And what else is going to move?
Plus 5. Or sorry, plus 2x.
We're going to do plus 2x. This term is going to move. Okay? Those were the two terms that didn't have a y value with them, so they didn't have a dy over dx. All right. So, I still have 3 dy over dx's, but at least I have them all together and nothing else in its way. Okay? How can we go from having 3 terms with a dy over dx to just 1 dy over dx. Anybody think of a way algebraically that we can do it? How can we condense it? What can we do with dy over dx since they all have it?
Taking dy over dx out.
We can take dy over dx out, and we're going to call that factoring. Yeah. All right, so that's number 3. We're going to factor dy over dx out. Thank you. So she's not here. No. All right. So this is just like algebraic factoring. I get it. Dy over dx, that's a weird term, but it's just like if this was any other letter. So we're just going to write, well, what's left? The 3y squared is left, the minus 2y is left, and then the minus 5 is left. So I factored that term out. I divided it out from all those. The right side, well, nothing's happened to that yet. We're just going to rewrite it. There was nothing to factor out of it. And so just to kind of recap what I did, after I took derivative, I bunched all the dy over dx terms together so that I could factor out dy over dx. This is what I'm trying to isolate. My final answer I want to be dy over dx equals something. That's what I want in the end. Okay? So what do you think my 4th step is going to be? Divide. I'm going to divide because I want dy over dx by itself. That's my answer. Remember, this is just like y prime. So before, we took the derivative and y prime was already by itself. We have to do a little bit more algebra here. And so the right side was negative 3x squared plus 2x. I divided by 3y squared minus 2y minus 5. And that's your answer. Even if you think you can simplify, don't. Most of the time you can't. Like in this case, there's nothing to simplify here. There's nothing that can be done. You could maybe factor something, but nothing's going to cross off, so don't even try to do it. All right, and you don't have to, so don't waste your time. All right, so this is what implicit differentiation is. Is it a little bit longer than the problems we've been doing? Yeah, it is, okay? But it's going to work out like this every time. In fact, if you turn the page, some problems are actually shorter. So if we look at number 3, that equation is actually way shorter than number 1. Okay, but we're still going to do the same steps. So what was the first step? Take the derivative of both sides. Now remember, this was d over dx. We're going to take that of both sides. Yes?
2y was an x, you would just do chain rule things.
Yeah, we're still going to do chain rule. But if this 2y was a 2x, we wouldn't, there's no y at all in here. This problem we really couldn't find the derivative. That wouldn't be a problem. It's going to need to have an x and a y in it. Yes.
Why is the graph there?
The graph is here. That's a good question. Let me go back to this one really quick and explain to you what we could do. Okay? We're not going to do it, by the way. What we could do is I could say, okay, well, let's take a point on this graph. It looks like 0, -2 is about a point. It's not exactly at 0, -2. But what I could do is I could plug in that point. In this case, we're plugging in the 0 in for x and the -2 in for y. We saw in our homework that before this, we were only plugging in the x value. We really weren't plugging in the y value. Now you've got to plug in both the x and the y. If I were to plug this in, I will get the slope. I will get the slope of this tangent line right here. So it means the same thing it meant before. It's just a much crazier graph. We're not going to do a lot with the graphs now, but I do want you to see all the different ways that these graphs look. It's just there to kind of show you that how crazy the graphs are. And on Monday, we're going to talk more about the graphs. and how they relate to the problem. All right, so like Rebecca said, we are going to do chain rule here. So first we got to take the derivative of the shell, which would be, yeah, negative sign. And remember the 2y is going to stay the exact same at first. Then we're going to multiply by the derivative of that 2y. What's the derivative of 2y? 2. And then I've got to have my dy over dx. Now you are multiplying all this. You can write the times sign or you don't have to, but we are multiplying everything. Okay, the right side though, we don't really have to worry about anything, just what's the derivative of x? 1, that's it. Okay, so how many dy over dx's are there in this problem? 1. So I don't need to worry about bunching them on the left, factoring them out. That's already been done. Like, this is the whole term times dy over dx. So I can go straight to the fourth step, which was divide. Okay, so that's my answer. dy over dx, the derivative of y with respect to x, same thing as y prime, is 1 over negative sign of 2y times 2. And you could move this 2 so that this said negative 2 sine of 2y. That would be fine, although what I've written here is fine as well. So this one's a little bit easier to find the slope. So I want to do that with this point right here. This is the point 1, 0. All right, let's plug that in. Remember, this is our x, this is our y. So if I were to plug 1, 0 in, I'm actually only plugging the 0 in for y. So that would give us 1 over negative sine of 2 times 0 times 2. Okay, well that's just 0. What's sine of 0?
1.
Think about the graph of sine. 0. Sine of 0 is 0. So this is essentially 1 over 0. That's an undefined. Well, look at the tangent line. What type of line is that? Vertical. So it makes sense that when you plug in those coordinates, you get an undefined number. Okay, this is those vertical tangent lines we were talking about. Like this point on the graph, you know, is we can't take the derivative. That's why this is an undefined number. Okay, and we could have taken any other points. This was just an easy one to plug in and a good review of that whole vertical tangent line thing. All right, now we're going to get to number 4. This is the last one we're going to do today. All right, but I will tell you it has its challenges. So I'm just letting you know now. I'm going to let you tell me what they are. Okay, first challenge. The directions are different. Find the slope of the tangent line to this function, or this is not a function. We can see here it's not a function at this point. So once I find the derivative, what am I going to have to do with the point?
Plug in x and y.
I'm going to have to plug in the 3 in for x and the 1 in for y. So that's the only way that you know, it's one extra step at the end. All right. I'm going to go ahead and rewrite this one over here instead of trying to fit in the d over dx. Because I don't want to know, like, if I go to 3, 1, like, I'll say this, if I plug in 3 in for x and 1 in for y, it'll just give me 2 equal numbers. It's just a point on the function. I don't really care about that. I want to know what is the slope of the tangent line. This is derivative language, so I have to do the derivative. I have to do the derivative first. If you plug in 3 and 1 right now, you end up getting 300 equals 300, which tells you nothing, because we already know 300 equals 300. All right. Okay, so starting at the left side, okay, we're going to have to do chain rule, right? So 2 times 3, that's going to be 6. The inside part, this is just chain rule right here. The inside part's not going to change. The new exponent is going to be 1. We could write it, but we don't have to. So that's the derivative of the shell. All right, times, now we got to take the derivative of the inside. That x squared plus y squared. What are we saying? 2x plus 2y. That's dy over dx. So there's my dy over dx equals. And then here's the next thing. 100xy. 100x times y. How am I going to find the derivative of 100x times y?
Just 100?
100 y.
If it was just 100, that would be lovely, right?
100 y gives the x.
Okay, I'm going to do it like this. It's a function, 100x, times another function. I have to use product rule here. All right, so let's just go for it. Whine later. What's the derivative of 100x? 100. Okay. Then we just write the y. Just doing product rule here. Derivative of 100x, then we just write the y. Plus. Now we're just going to write the 100x and take the derivative of y. Well, what's the derivative of y? 1 dy over dx. Okay. So that wasn't too bad, right? We had to do product rule, but it wasn't too bad. So I'm going to circle the dy over dx's. I have two of them. So this one's different. We haven't done one like this yet. Dy over dx is on both sides. Although that's really just an algebra thing. Okay? I need to get dy over dx only on the left-hand side, and I need everything else that's not directly multiplied to a dy over dx to the right-hand side. So here's my next little situation. How am I going to get rid, this 6 times x squared plus y squared is being multiplied to this entire thing. One of the pieces I want to keep. The other piece, 2x, I don't want to keep. This is a problem. Okay? There are multiple ways we could deal with this. What I'm going to suggest is that we just distribute so that they're not locked together. Okay? We're not going to simplify as we go, so it's going to be more writing, but it's not going to be difficult. So watch this. I'm going to distribute that there, and then I'm going to distribute it here. Okay, so I'm going to write this down. 6x squared plus y squared times 2x, okay, I distribute it to the first thing, plus, now I got to distribute to the second term. 6x squared plus y squared times 2y dy over dx. Okay, so now the whole reason, if you're thinking, why did I need to do that? Well, in order to get my dy over dx's together, this was always going to be a problem right here until I broke this up right here. This plus right here, I couldn't just subtract the 2x when I have something in front of the parentheses. I had to do this algebra step. All right, I'm going to go ahead and just rewrite the right-hand side. Everything that's complicated about this problem at this point is algebra. It's not calculus. It looks like calculus, all right, but I'm doing algebra here. It's just a lot of it in one problem. All right, and I give you that. It's a lot of algebra in one problem. So let's circle our dy over dx's again. Okay, we still have the problem. They're on two different sides. Okay? So don't just write down what I'm writing down. Really think about this. I want this term to stay. So let's write it. 6x squared plus y squared times 2y dy over dx.
Why didn't you just divide both sides by 6 x squared plus y squared?
If I had up here divided both sides by 6x squared plus y squared, it would take care of the problem here, and it would create a whole brand new problem over here. Because then I would have that 6x I would have this term connected to this dy over dx. So I could have done that. It would have been, in the end, messier. So I just decided, let's distribute. All right, so I need to subtract over my other dy over dx term. So that's going to give me minus 100x dy over dx. The non-dy over dx terms, they got to go to the other side. Okay, so I already have 100y. That's exactly where I want it. The other term I got to subtract. Now, at this point, I know this is messy. I know it's a lot, and you're probably thinking, is every problem going to be like this? Well, of course not. We've already done two that weren't quite like this. But do be happy that you don't have to simplify, at least, right? It's just a lot of writing. Okay, I think, let me circle dy over dx. Are we ready to factor it out?
Yes.
Yes, finally, right? dy over dx. Okay, you don't need to look up here and copy what I'm doing. Look at your own paper and write down what you have left. So you're factoring out dy over dx. Write down what you have left when you take those away. It is a lot of writing. I've done this problem 3 times today alone. I get it. At least y'all don't look like you're about to throw your pencil at me. Not there, period. Fine. Okay, we are really close to being done. What's the next step to getting dy over dx by itself?
Divide.
I need to divide. Again, you could simplify this, and you don't have to. This is a really messy problem. I want you to realize that. I like doing this problem in notes, though, because it's kind of like, am I going to do a whole bunch of problems, or am I going to do some where we can talk about things like product rule and distributing and all that kind of stuff.
Is this worst case scenario?
I wouldn't say this is worst case scenario, but it's pretty long.
I mean, like, that's what I did.
Yeah.
Just don't, right, today I don't want y'all to worry about what's on the test, what's not, because it's just a bad place to go, right?
What about home?
Just, you'll know when you get to your homework. Okay. Now, the reason I said we were almost done is because I did find the derivative, but I actually didn't do what they said. So I still need to do one more thing. Thought you're done, right? Okay, but here's the nice thing is, you want to get your calculator out and do the number crunching, feel free. Okay? By number crunching, I mean we're plugging in the 3 in for x and the 1 in for y. All right? I'm going to erase some of this so that I can write that down. I mean, I was writing really big so that you could see everything nice and neat. All right, so I'm going to go back here, and my slope at this point is going to be 100 times 3. Oh, not 3. $100 times 1 minus 6 times 3 squared plus 1 squared times 2 times 3. I made my first period class do all this without the calculator. It's the afternoon. It's not that hard. Listen, a student in elementary school could do this. You could do it. It's not that bad of number crunching. It's really, none of this are numbers you can't, it's just adding and subtracting and multiplying. But I get it. It's afternoon, don't want to do it. Feel free to plug it in your calculator. So you got to do one or the other. You're either going to do it by hand or do it on the calculator. Or I guess just look at me awkwardly until I tell you the answer. I already did this today.
I've never played that.
Oh, that's how you rate for There's always a moment where you're like, oh gosh.
13 over 8, 9.
13 over 9. That's close. You weren't even writing it down. Were you doing that all in your head?
No, no.
Or you wrote it down?
I did a lot of math.
You did?
I
Okay.
can do that.
Are you kidding me? Well, that's why I was like thinking, man, that's crazy. All right, it is 13 over 9 when it simplifies, okay? So what this means, hang with me this last second, and then we'll be done a little bit early. So watch this. It means that at this point, 3, 1, the slope of the tangent line is 13/9. That's what that means. It means the same thing we've been doing this whole year about slope of tangent line, or since we've been doing derivatives anyway. That's what that means. It's just now we're dealing with implicit functions, or not functions, but implicit equations.
We have lost